around that, like that, around the edge of a donut. That's an interesting approach. What I'm getting at is that you can't just arbitrarily go from any surface integral to the divergence theorem, right? The condition is that this surface encloses a solid. If it doesn't, then you can't. Because then, I mean, if it was always, right, if this was always the case, then wouldn't it be nice if we could just say, hey, look, if you want to do work, you can do this, but then wouldn't you be able to just take the div of the curl? Right, because this is our new field, right? And then just take the div of that new field. So the div of the curl would give you the same answer. But we don't have that. So I just wanted you to think about it. Just make sure you understand these important theorems only work when the surfaces and the curves have certain conditions met. In this case, we have to have that surface encloses solid. All right. So what we're going to do now is we're going to go back to Chapter 13, Section 7, and we're going to look at this problem here. So I don't know, maybe you'll see that in your notes somewhere. We did this problem?
Yeah.
Do you have it there? Is it like one page? About a page?
About a page.
It's about a page. And what was our answer?
Negative pi.
That was there were two answers. We had to do two surfaces.
Oh, yeah. Zero.
Yeah, this was that one we were trying to compute the flux, and I said that the flux came out to be 0, right? And we were talking about, well, that's kind of weird because like this back surface, I don't remember if the back surface was pi or negative pi. This was negative pi and the front surface was pi, so they cancel each other out. But we did quite a bit of work to get it, didn't we? Okay. Do you all agree that the surface, right, this surface, the green and this brownish, yellowish one in the back, do you agree that it encloses a solid? Yes? So, and we're trying here to do flux, aren't we? Find the flux. So what I'm going to do here is instead of finding the flux over this surface, right, we're trying to find the flux over the surface of f dot ds, right? That's what we're trying to do here for flux. Instead of doing that, I'm going to use a divergence theorem, triple integral over E of div f dv. Now, E is the solid that this encloses, right? And we all agreed that there's a solid there that this surface encloses. What's the div of f? So do y'all remember how to compute div of a field? Curl of a field sucks because you have to cross, but this one is real easy, right? What do?
Partial of the x component with respect to x.
Yeah, you take the field, right? You take the first component and you take its derivative with respect to x, which would be? 0. And remember, the div is a scalar. It's not a vector. Then you add to that. Now you go to the second component, q. Take the partial with respect to y, which would be 1. And then you add to that. Now you go to the third component, take its partial with respect to z and get negative 1. And all that adds up to be 0. So you're winding up, this triple integral becomes the triple integral over E of div of f, which is 0 dv. And the integral of 0 is always 0. And we're done. That's the answer that took us a while to get, right? So obviously the divergence theorem was useful here, right? We got to it very straightforward. So on an exam, if I were asked to find the flux and I see a surface and I see it encloses a solid, I'm going to go for div first, right? I'm going to go for divergence theorem first. Now, if I just wanted the back part and there was no green, then you couldn't use divergence theorem. This is an interesting idea. Okay, are we good with this?
Yep.
Okay. I want you to consider something for a second. Let's say we're sitting here, we're looking at this problem. let's say that I'm asking for this flux, but I just want it over this back region right here, just that back region, okay? If I want it over the back region, then I can't use the divergence, right? But if I look at div, even though I know I'm not allowed to use it, if I look at the div of f, I know it's 0, right? Which means that if I were to close it, right? Imagine this green thing isn't there, right? So it's like this. What I know is that if this was closed, right? If it was closed, the answer should be 0, shouldn't it? So what I could do is I could say, all right, instead of trying to find the flux through this back piece, which might be some work, what I can do is I can find the flux through that piece, which is a plane. And what can you tell me about the flux through each of those? They must add up to be 0, right? Which means they are opposite of each other. So in other words, you could just go find the flux through that flat plane, and then whatever the answer you get there, this one will be the opposite of that. But that would all be based on the fact that the div was 0. I'm just kind of pointing it out, like that you could kind of use the div still to do this. Yes?
So what you're saying is we could assume it's closed at first, find the div, and we find out it's 0, then we can just assume that the two of them cancel out.
Yes, which means they're equal opposite.
Okay.
Yeah, exactly. That the flux through one is equal to the opposite of the flux through the other. So if one of the surfaces is easier to get the flux of, go get that one.
Yeah.
And then the other one's answer is just the opposite.
Okay.
Yeah.
Won't that only work when there's 2 surfaces? Like what if we have?
Yeah, if you had more, yeah, if it was 2 only. Yeah, if it was 3, then, yeah, no, you couldn't. What I was trying to do is point out how you could still theoretically use div in this problem. If you were only asked for the backside, you could. All right, so how about this one right here? Can we use it here? Now we did this problem. Please look in your notes. We did this one. This one took us a while. There were 4 surfaces, right? There was the front side, there was the back side, there was the bottom, there was the top, right? And I think we got something like 2/3 plus pi, something like, what was it?
2 pi plus 8/3.
2 pi plus 8/3 is what we got when we added up all the flux through this whole thing. But now we have a solid, don't we? We have a solid here. Boom, there it is, E. It's enclosed by all those surfaces. I can use the divergence theorem. So I'm going to just go get the divergence first. Okay, I want to get the divergence first. Because if I look at the divergence and it's really ugly, I may not even want to do it. But the divergence here would be, I just do the partials of each one, right? 2x, add, 2y, add, 2z. Now look, it's not as good as 0, okay? Like the previous example, but it's not like horrible. So what I know is that the flux through the surface, through all 4 surfaces together of f dot ds, I know that that's the same as the triple integral over E of the div of f dv, right? The div of f is a scalar function, right? It's scalar. And then with respect to v, this is the good old-fashioned triple integral. That's all it is, good old-fashioned triple integral. No vector fields, right? There's no vector fields or anything in here. Everything is scalar now. So I would like to see if there's an easy way for me to define what E is. Remember, because if you're trying to do a triple integral, you need to somehow come up with restrictions on x, y, and z, right? To somehow, get your little inequalities here. So when you look at this, how do y'all want to do it? There's a couple of ways to do it, so it's kind of up to you.
Let's look at x. Right, we got the boundary of 0 to 2.
0 to 2 for x, do y'all agree? X is between 0 and 2. Y is between, I think it's -1 to 1. We can tell, yeah, if we go back in our notes, this, when we solved it, it had a radius of 1. So negative 1 and 1 for y. And z is between where? 0 to the top surface, right? The top surface is square root of 1 minus y squared. There we go. So we can set this triple integral up and we're off to the races. Yeah, your dz has to be first. Good. Because this one has a variable. So I'm going to do this. I'm going to go integral. I'll go 0 to 2. So I'm going to do my x's last. I'm going to go negative 1 to 1. I'm going to do my y's next. I'm going to go 0 to root 1 minus y squared. And then what am I actually integrating? 2x plus 2y plus 2z. How about I do this? Pull a 2 out and just make this x plus y plus z. d z d y d x. We could do this, yes? I mean, it's not fun, but we could do this. I don't really feel like doing it, but I'm going to do it. I don't feel like doing it, but I'm going to. I want to show you that there was another way to define this e, not doing it this way. And I think this is the way most people would do it, like initially. Yeah. But another way we could have done it is this. Look at this solid as, can you see it as a polar region? Look at the backside here. Do you see that backside? We project this over, you got a polar region there. But in what two variables? The y and z. This is y and that's z. So what I could do is I could go to polar here. I could let y be equal to cosine, it is a radius of 1, right? So r cosine, r cosine theta, let my z be r sine theta. If I do it this way, then what's my, I have restrictions now on r, right? Between 0 and 1. Theta between 0 and 2, not 2 pi, sorry, 0 and pi is only 1/2 of it, right? And now I need to draw the solid. So my x, right, is the thing that goes back and forth. My x is between 0 and 2. Do you see that? And now you have constants everywhere. And that integration is probably going to be a little easier. Yeah. What would this triple integral look like, though? It'd still be this, it'd still be the x plus y plus z, right, with the 2 pulled out? Yeah. So 2, I'll have 3 integrals. Okay, doesn't matter. 0 to pi, 0 to 1, 0 to 2. Okay. So x plus, so x we leave as x, right? Because x is between 0 and 2. So x plus y, what's y for us? R cosine theta plus z, which is r sine theta. And then all of this is going to be r dx dr d theta. That should give us, I'm not sure the integration is that much better, but I mean, I don't want to mess with square roots and stuff, you know? So this is doable. Now, I'm going to do it, okay, on the calculator. I'm not going to do it by hand. But I'm going to do them both, just to show you that we should get the same answer both ways, all right? What do you want to calculate? I want to do an integral. No. Definite integral. And then another one. And then another one. It's kind of weird how they do that, huh? All right, let me do the first one. Put the 2 out here in front. We're going negative, or 0 to 2. Negative 1 to 1. 0 to the square. square root of 1 minus y squared. And this is just x plus y plus z dz, dz, dy,
Yep.
dx. See, if you're using a computer, then really it doesn't matter which way we do it. There it is. Distribute the 2. 8 pi, or 8 over 3 plus 2 pi. Okay, we get that. Now, let's do the other one. The other one was 0 to pi, or I did pi first. So pi, 0 to 1, 0 to 2. And then this was x, this was r times cosine, doesn't matter, cosine of t, I'll use t instead of theta, and then r, let's see, times sine of t, dx, d,
We need an R.
oh, I'm missing my r, thank you. Oh, I forgot it. Good thing I'm not taking a final. dt, all right, so r out here in front, r times, okay, there we go. There it is. There it is right there. Same answer. As it should be. Okay? All right. Let's see. What else we got? There was one more problem that I want to do, and this will be our last problem of the semester. It's one of them out of the book for 12.9 or 8. Yeah, 12.9. No, 13.9. I better do this before my brain goes completely. At the end of chapter 13, section 9, the very last page, it has a summary where it shows a picture of like your good old-fashioned Cal 2 integral. And then we learned about line integrals, and then we learned about double integrals and Green's theorem, and then Stokes' theorem, and then divergence theorem. It's just a nice little summary in one place to look at kind of like everything this is not everything we've done, but it's kind of a good little summary of this last chapter. Okay, so where's the one I liked? It was a box. Which one? Okay, I've never done this one, so this will be fun. I'm trying to pick one that I've never actually done on camera, so this will give me an opportunity to mess it up. Well, I'm erasing this. I'm not sure how much I'm going to be able to get an honest opinion from you, but you know, I've done this class before where I didn't do the mini exams, and it's more of like your traditional class with more exams, right? More in-class exams. The mini exams for me have always been like, y'all are Cal 3 students. This is the end of the calculus sequence. You should be thinking at a certain level on things. So I was looking as a way to push. But I'm starting to get this feeling like people are hearing about these mini exams and they're like, nah, I'm not going to take the Cal 3. I know. What do y'all think? Do you feel like you're walking away with the mini exams as being beneficial, or just more of like this thing that was a pain in your ass? This is why I don't know if I can get a good, honest opinion right now. Interesting?
I actually like them more.
Yeah.
Honestly, if you paid attention to the homework, when you did your homework, the exams kind of just flowed right into it.
Especially at the end. Especially at the end. I mean, it's pretty much homework problems.
Yeah.
But, yeah.
It's kind of like a curtain.
Yeah.
They hear about the mini exams, you see the mini exams, you're like, oh my god. But if you actually just did your basic
Yeah, you're talking for me. Thank you very much. I appreciate it. But I told you all that in the beginning, though, right? I said, hey, look, you know, mini exams, you got to do your homework, though. If you just go straight to the mini exams and you expect to understand what you're doing, it's going to be a lot harder than if you do your homework first. But that means you have to do a lot of work, right?
Yeah.
But this is Cal 3, right? So it's kind of to be expected. Okay, so we've got a field here, right? And then we've got this surface, S, and let me tell you about this surface. It's a box, okay? The surface is a box that's enclosed by the planes. Here we go. X equals 0. X equals A. Y equals 0. Y equals B. Z equals 0. Z equals C. Where A, B, and C are constants. And they're positive. So here, A, B, and C. A, B, and C are all greater than 0. They're all numbers and they're all greater than 0. So what we want to do here is we want to calculate the flux. Find the flux through the vector field over that surface. The flux of the vector field through that surface. All right, so let's draw this first, right? Let's draw the S. Let's see, this is X, this is Y, this is Z. So the planes, do y'all see this box? Do y'all see how this is going to be? You have X equals A, Y equals B, Z equals C. So they're positive constants, A, B, and C. Imagine all these planes. X equals 0 is the ground. Oh, no, sorry. Z equals 0 is the ground, right? Then you have X equals 0, Y equals 0, the coordinate planes. And then you have X equals A, which is a plane that comes out this way, slices this. B comes out this way, slices here. C is up and slices. So it's a box, right? It's a box. It looks like, let's see. It looks like this, roughly. There it is. I think this problem is going to wind up being pretty simple. Let's see. Is that surface S, does it enclose a solid E? Yes. So there's my E in there. And that E is super easy to define, isn't it? So I'm going to go ahead and use my divergence theorem. It's triple integral over E of div F dV. And I need my div F. Please be good. Please be good. Partial of this with respect to X. 2xy. 2xyz, sorry. Plus partial of the other one with respect to y. 2xyz again. And last one, 2xyz again. Those all add up to be 6xyz. Not terrible, not terrible. And so now I need to see if I can somehow define what E is. E is, I think, pretty easy to define, right? Your X's are between 0 and A, Y, 0B, C, 0C. I mean, sorry, Z, 0C. I can't talk anymore. They're all constants. So 0 to A, we'll do that one on the outside, and then 0 to B, and then 0 to C. And we're integrating 6xyz. Pull the 6 out. xyz in here. dv. No, we'll put our actual variables. Z first, then y, then x. No need for polar here. No, you wouldn't even want to do polar. You don't have any polar anywhere, do you? Nothing looks polar. And that's it. Crank it out. Crank it out. Hey, can I do this? I'm just curious. Can I do this? I mean, I could go to the computer, right? But am I allowed to do this? Could I do 6 and then integral from 0 to a of x dx times integral from 0 to b of y dy times integral from 0 to c of z dz. What do y'all think?
Yeah.
Yeah, because the x, y, and z are all separated by multiplication. So the limits of integration are constants. So we're allowed to do that, right? And so if I do one of these, they should all have the same format, right? What's the antiderivative of this? 1/2 x squared. And then you plug in a for x and plug in 0 for x. So you just get 1/2 a squared over 2 times b squared over 2 times c squared over 2. 2 times 2 times 2 is 8, right? So 3/4 a squared plus b squared, I'm sorry, a squared, b squared, c squared. There we go. I think that was pretty straightforward. Shall we check our answer? Not with the computer, I'm going to check with my solutions. I have a solution manual somewhere. What chapter is this, 13? Should be at the very end. Why is this not? This was number 4, I think. No, number 6. Yeah, it's right there. Can you all see that?
Yeah.
Where the hell is it? Right there. That's it right there. 3/4 a squared, b squared, c squared. All right, are y'all good? Are y'all happy? Y'all want to wrap up or you want another example?
No.
You're done? We're done? Okay. All right, let's be done. Let's talk about the final. So I'm going to bring up the review I gave y'all. I was talking to my Cal 2 about this. Remember, the review / mini exams, right? The things that are, remember that's a guide, right? You're supposed to look at that and then look at your homework problems as well. What am I doing? This is what I gave you, right? That was it, right? I gave you all my spring 2023 final, right?
Yeah.
Okay. So is there anything on here that I can talk to you about? Hey, we finished the book. Yeah. It's good. Lagrange. I'm not going to work through any of these. I mean, I'll talk about them, but I'm not going to work them. You can do them on the page or you can do them separately. It's totally up to you. So make sure your name is somewhere on it. It's legible.
For me personally, I think the most difficult thing about this was Lagrange for me.
The Lagrange?
Yeah, because remember how it's the concept of you don't know when to stop? So,
Yeah. Like, have you checked everything?
yeah.
Well, the good news about this one is at least it's a single function with a single constraint. It is three variables, so you're going to have four equations you have to satisfy, right?
Yeah.
The gradient, the partial of this with respect to x must equal lambda times partial of this with respect to x, and then. So Lagrange is going to definitely be on the final. without a doubt, because that wasn't on your midterm, so it's going to be there. This one, it's just to make sure you know how to set up a triple integral, right? I mean, this is not, there's no voodoo magic here, all right? We can talk a little bit about it. What do you wind up using here?
Polar.
You do wind up with polar, don't you? I mean, that's probably your best bet here. Go to polar here. So, problem like this just checks that you know how to set up a triple integral, that you know how to do polar regions, right? This one, asking for what? Work, right? Work. But your curve is not closed. And since your curve is not closed, you are forced to use the formula, right? But the good news is I give you what R of t is, right? So you can easily find its derivative, and then you do the field evaluated there, and evaluate the field on the curve. And so I think it's really, when you look at it, it's like knowing what to do, right? That's what it's about, like knowing what to do. So let's see. This one is a little confusing because you can go down the wrong road here and waste a lot of time. So first thing I do is I say, hey, find a function f such that the field f that I've given you down here is the gradient of that function, the scalar function. So I'm asking you to find what we call the potential function. So you have to find the potential function, which we did in class. That was called partial integration. Okay, so we did that. We found little f. Then I said, use what you just got, little f. Use that to find this. Don't be using the little f to do anything other than find that. So that's a hint to you to not go grind this out the way you just did the previous problem. Use what you just did. So you have to understand there's a connection between this potential function and a line integral, and that is the fundamental theorem of line integrals. That if you're trying to find a line integral, then if you know the potential function, then the value of the line integral is equal to the value of the potential function evaluate the endpoints of the curve that you're given. And I give you the curve, right? I give you the curve. I don't give you the endpoints. But you can get the endpoints by just evaluating it at 0 and at 1. That would give you the two endpoints. So the hardest part of this problem is finding the potential function, if that's even hard. And then the other hard part is knowing what you do with that now, right? So what I'm warning you against is don't go try and do this the hard way, the grind out way. If you take this curve and plug it into the field and then dot that with the derivative of that, then, have fun. You're working hard, not smart.